So now we're going to review the fundamentals of electrical activity in the heart. So there are two types of cells within the heart. Each of them has their own unique electrophysiology. There's the cardiomyocytes, which are the muscle cells of the heart, and then there's the cardiac pacemaker cells, which are the cells mostly in the SA and AV node. It's important to remember that all of the cells in the heart are connected by cellular bridges called intercalated discs. This is important because it makes depolarization and repolarization easier for the entire myocardium. This allows the heart muscles to function and contract as a single coordinated unit. Understanding the electrophysiology of the myocyte and the pacemaker cell is critical to understanding electrocardiograms and cardiac arrhythmias. Before we really dig into the information here on the slide, let's go over two key terms. I remember when I was a medical student being confused by the terms depolarization and repolarization. The way I have wrapped my head around this, and the way I hope to help you understand these two terms, is to think about de and repolarization as either going away or going towards the cell's resting membrane potential. Let me explain. So cells in the body are polarized, meaning they have a negative resting potential, generally negative resting membrane potential, based on the relationship between intra and extracellular charges. In general, cells are negatively charged with a resting potential in the heart, for example, at negative 85 millivolts. So that is when the cell is at rest. It is at this negative 85 millivolts. Now, when I say depolarization with a D, I'm referring to the process in which electrolytes are coming or leaving the cell so as to bring the membrane potential away from its resting potential. So it's being depolarized. It's moving away from this baseline of negative 85 millivolts. It's depolarizing in general to a more positive membrane potential. When we talk about depolarization in general, we're talking about an increase in membrane potential closer to zero. For instance, when sodium, a positively charged cation, enters the cell in phase 0, which we'll talk about in a moment, the resting potential rapidly increases from negative 85 to greater than 0. This is sodium entering the cell, crossing the cell membrane, going from the outside to the inside, and causing the cell to be more positively charged and closer to 0 millivolts. This is being depolarized. We are taking away the cell's polarization. On the contrary, when potassium, another positively charged cation, flows out of the cell, say in phase 1, potassium flows out of the cell in phase 1, the cell is becoming more negative. Positive charges are leaving the cell is becoming more negative, it's approaching negative 85 millivolts again, so it's being repolarized, or it's polarizing again. So when sodium enters the cell, it's depolarizing it, taking it from negative 85 towards 0. When potassium leaves the cell is being repolarized and bringing back down from, say, 0 millivolts back down to negative 85 millivolts. So I hope this simple explanation makes some sense, and hopefully you can remember the term depolarization and repolarization conceptually, because I'll be using it frequently during my explanations of the myocardial action potential. The action potential of the cardiomyocyte is called the myocardial action potential. The myocardial action potential is broken up into 5 different phases. 5 different phases numbered 0 to 4. Each phase is characterized by a change in the cell membrane potential secondary to movement of a particular electrolyte into or outside of the cell. That's really the key here, is that each phase represents a change in membrane potential throughout the action potential that is ultimately caused by some sort of movement of electrolytes through some channel in the cell membrane that results in a change in the membrane potential. So let's start and go through each of these phases one by one. Phase 0 is the beginning of the action potential. It's called the upstroke, because this corresponds to this very quick, or you could say rapid, increase in cell membrane potential, basically from negative 85 up to greater than 0. This corresponds to the opening of fast, voltage-gated sodium channels. So the key here is sodium channels open, resulting in a rapid depolarization as a result of inward movement of sodium. The positive charged sodium is entering into the cell, depolarizing the cardiomyocyte. So the slope of this phase zero is directly proportional to the net ionic current provided by this sodium influx. It really goes straight up because sodium is rapidly moves into the cell through voltage-gated sodium channels. These voltage-gated sodium channels open in response to the impulse action potential generated from the pacemaker cells of the SA and AV node. So crossing over quickly into pharmacology, these are the channels that your class 1 antiarrhythmics work against. They block these sodium channels. They decrease the slope of your phase zero. To decrease the slope of your phase zero, increasing the duration of your action potential and working as an antiarrhythmic. So after the cell is sufficiently depolarized, potassium channels open in response, and there's a quick outflow of potassium as well as a decrease in sodium influx, and this is known as phase 1 or early repolarization. So you can see this black line here represents a quick and dirty repolarization of the cells. The cell and membrane potential is decreasing, say from 10 millivolts here to about 5 millivolts there. It is repolarizing because less of sodium is entering the cell and the voltage-gated potassium channels are beginning to open, resulting in potassium leaving the cell. So you have a decrease in sodium influx, an increase in potassium efflux, and that results in a brief period of repolarization, and that's phase 1 of the action potential. This repolarization is stopped pretty quickly, and we enter phase 2 of the cardiac action potential. Probably the most unique feature of the myocardial action potential is this phase, and it's called the plateau phase, or phase 2, plateau phase. The plateau phase is defined by an influx of positively charged calcium. It's an influx of positively charged calcium into the cell, as well as an efflux, or a corresponding efflux of potassium outside of the cell, causing a plateau or a flattening of the cell membrane potential. It is isoelectric. There is no change, or very minimal change, in the membrane potential during this phase, because we have both calcium influx and potassium efflux that are balancing each other out. So this is the critical part of the plateau phase, is you have calcium inflow and potassium outflow that are equal to each other, and this keeps the membrane potential positive for a short period of time, and we have a large influx of calcium during this time, and that initiates and contributes to the forceful contraction of cardiomyocytes. So you have increased calcium here that causes an increased contractile force of the myocardiocytes. So when we look here at this image, we can see the sort of a diagrammatic, we can see a diagram of the cardiomyocyte here with all the channels that are important to the cell. And we can see this calcium entering into the cell from the T-tubules through these calcium-induced calcium channels. And this results in binding of the ryanodine receptor. And this causes the calcium from the sarcoplasmic reticulum, an area of high calcium concentration, to be released into the plasma space of the cardiomyocyte. This significantly increases the cytosolic calcium, which subsequently increases contractile force generated by the cardiomyocyte. So we can see here with this graph, we see the action potential is the black line. We see that upstroke. We see the early repolarization, the plateau phase. During that plateau phase, we see this large increase in intracellular calcium, which is this purple line. As a result, we see this increased contractile force that comes right after in the green dashed line. So we can see how these all work together to cause a contractile force of the heart to pump blood effectively throughout our body and perfuse our vital organs. The next phase is phase 3, and this phase is called the rapid repolarization phase. And this phase occurs when all of the L-type calcium channels, which were open in phase 2, have closed, and the only channels that are still open are the slow delayed rectifier potassium channels. The slow delayed rectifier, these are the only channels that remain open, and this results in efflux of potassium, resulting in repolarization or approaching the resting membrane potential. And finally, once we reach the bottom of the myocardial action potential, we enter back to our resting membrane potential, also known as phase 4. This is our resting membrane potential. In this phase, it is not the rectifier channels that are open, rectifier potassium channels. It is the inward rectifying potassium channel that is opened. I'm not trying to confuse you, but there's a couple different terms here. In phase 3, you have the slow or the delayed rectifier channel that opens. And then here in the phase 4 part of the myocardial action potential, we have the inward rectifying potassium channels. So these are different potassium channels. The phase 3 and phase 4 are different potassium channels. It's sort of a minute point. It's not the most high yield piece of information from the slide, but it's important to point out for the sake of accuracy. And these potassium channels that dominate in phase 4 actually allow some potassium to come back into the cell. So they actually let potassium come back in, which is unique from typically potassium leaves the cell. But it works alongside the sodium-potassium ATPase to restore intracellular potassium and maintain the negative resting membrane potential between -70 and -90 millivolts, which is our resting membrane potential of a cardiomyocyte.